Aren't those the same thing?
Yeah, right? Aren't they the same thing? Depends on what, and this is what we want to, this is what I want to talk about. It depends on what you want to do with it. Okay, so let's think about if you have something that looks like this, and you want to do implicit differentiation versus something like just get y by itself.
Yeah.
For whatever reason, you might want to get y, or maybe it's not y. Maybe it's something else that's something else locked up inside of an e that you want to try to get out of there. There's two different ways of going about this. Although you'd use both ways. I mean, the same thing to do the same thing. Well, but if you're not trying to take a derivative here, right? That's kind of what I'm getting at. Like on one hand, you're trying to take a derivative of stuff. On the other hand, if you're just trying to get the y by itself, we're going to do some different things. So let's say we want to take we have this relationship, and we want to take the derivative of the entire thing with respect to x. What happens over here? Let's say I take the derivative with respect to x. What happens?
It's
y to the y.
E to the y
prime.
times, good, y prime, right? It's the chain rule, right? Because if this is some function of x, right, and we take the derivative with respect to x, we take the derivative of the outside stuff, leave the inside stuff alone, multiply by the derivative of the inside stuff. And that's all that's going on there. We're treating implicitly, we're treating y as a function of x, right? Okay, and so then what happens on the right-hand side?
It's
F
just
of
f
x
prime of
dx.
x.
Just f prime of x, right?
Yeah.
Or we could have done this as e to the y dy dx equals df dx, right? Just different notation, means the same thing. Right? Okay. So that's how you deal with that. Now let's say we don't want to take any derivatives. Everything's in the way that we want it. We just need to get y by itself. What do I do? Natural log of both sides should do the trick, right? And we take natural log here, and then what?
Drop the y down.
Right, the y drops down, and it's that.
Divide.
Or you could just think about it as that's the inverse of e to the y, right? That's arc e. Although, I mean, it is true that that's the case, but that's just one,
Yeah.
right? So, right, but that is arc e. Log is arc e, or e is arc log. I like that, arc log, right? Arc log of y, log of arc log of y is y. So then you have this over here, log of whatever this stuff is. Okay? Now, one thing to notice is we could have also done that over here. Right? Remember, we could have said, well, if I could just get the y by itself, right, then I could take the derivative of it, and you would have said, well, to get the y by itself, I just do this to both sides. Whatever it happens to be, and that's what gives me my y. And then I take the derivative of both sides, that gives me y prime is equal to, now what's the derivative of this?
1 over
1 over the stuff
Times
log
f prime.
times f prime of x. And then it looks different, but if we rearrange this, bring the f of x upstairs. F of x was, in the very beginning, equal to e to the y, right?
Yes.
From the very beginning. So that's e to the y, y prime equals f prime of x. Okay, so implicit differentiation, if you have something involving an e, you could do the log thing, and that might make your life easier. You could just go ahead and do it, right? And that's just true if it's e to the y. With implicit differentiation, in general here, you have some function, maybe involving x and y, equals some other function involving x and y, right? I just didn't put an x up here. If I put an x up here, then we would have had something different. Or if this f of x happened to be an f of x and y, maybe it's xy plus square root of x plus y, or something like that. But in both cases, what you do is you take the derivative with respect to x, and then multiply by whatever the derivative of y is, right?
Yeah.
And then same thing here, times y prime, and maybe whatever, and then you try to get all the y primes by themselves, whatever. Okay? But my point here, and what's going to be important, is that you recognize, like, if the thing that you're not trying to take a derivative of that thing, because there are two questions involving implicit differentiation, and whatever, you know, do whatever you want, it doesn't matter. But then there's one question on there that you might be, since you've done these implicit differentiation questions, you might just blindly plug along and take a derivative and do a bunch of stuff, and then that's going to make your life much worse. And so what I'm saying is, you have this, don't think too hard about it. This is what you're looking for. If your point is, man, my life would be really easy, there's something up here, it would be really easy if I could get it by itself, well, yeah, that's what you do. Okay, so that's one thing I wanted to say right off the bat before we actually go into everything. Another thing I want to say. So I spent a long time doing this. Like, I put a lot of effort into this, as you'll see, especially at the end. There's this one, and as I was going back through it, working out these problems, I realized that there's one problem in here that would be wicked hard if you don't do this easy simplifying thing. I don't want to give too much away. I'll just say this. If at some point you end up with something that looks like this, and it might not be an x, it might be a different variable that you're working with, but if you have something that looks, oh, I don't know, and now this is not going to be exactly what it looks like, but maybe you have something like this. I don't know, and let's make it a 3. And then you're about to do something to this. If you just plug along with it this way and do the thing to it, maybe it's derivative, maybe it's an integral, whatever. Oh man, although if that were an integral. Anyway, it would make your life really hard unless you take this, because this is when I was coming up with this problem. I just naturally said, you know what, my life would be easier if I just do this. And then just bring him in as an x squared. That way I'm dealing with one root and not a product. Which is the same thing as in this case, x to the 7th plus 2 over x. Now, if I were taking a derivative, I would just take the derivative of this. That makes life way, way easier. Right, because if I were to, say, take a derivative of this, I would just, the way I do these, I go, oh, a root, okay, so it's whatever's in the root, and then I just take the derivative of the top stuff, right? Yeah. In this case, I guess it would be 7x to the 6th minus 2x squared, something like that, right? Maybe you don't even care what the denominator is in this case, for whatever reason. That, then, you know, plugging along that way will make your life much easier than if you needed to take the derivative of this. Well then, okay, the derivative looking like this, you'd say, okay, product rule, so it's going to be that goes down to that. So the derivative of x is just 1. Add that to, leave the x alone, and now take the derivative of the rest of the stuff, and so you have this, and then the derivative of that would be 5x cubed. Minus 3 drops down, right, because that's 2x to the minus 3. The minus 3 drops down, giving you a minus 6 x to the minus 4th, so then there you go. And the thing is, after plugging along, you'll get to the same place, regardless of which way you go. But this, I was like, oh, what if I didn't see that? what if they did it this way? And then I started plugging along. I was like, oh no, that's really hard to deal with. And I didn't think it was going to be that way. So I just want to go ahead and give you a heads up. If at some point you're trying to do something like this, go ahead and bring him inside. It might not be x's, it might be a bunch of other stuff, but this is the idea, is that if you're trying to take a derivative of something like this, if it's just one root, your life's much easier.
Yeah.
Okay, and that's one of those things. And I didn't even notice that I was doing this step right here. It's just that I've done so many derivatives involving roots that I know that this leads to this, whereas if I bring it in, I have one root. And so I wasn't even conscious of that when I was coming up with this problem, or working out this problem. And so I thought, oh yeah, it's super easy. And I thought, ooh, what if they just do the, oh no. Okay, so those are like a couple of caveats I wanted to give you before we actually start talking about this stuff. Okay, so one thing you're gonna need to know is the definition of a derivative, right? So let's just think about what that is. F of x is equal to what? It starts with the L.
Oh, the limit
Uh-huh.
as x goes to 0. H goes to
There we go. That's how we usually do it, is with an H of what?
f of x minus g of x. Wait.
Minus 8. No.
What? I'm just writing down what you're
F
saying.
of x plus h.
F of x plus h. There you
Minus
go.
f of x
Minus f of
over
x.
h.
Now that's how we've set it up, right? That's how we set it up. That the derivative at x, you have some function. You want to know what's the slope here at some number x. And so the way that we set it up is you say, okay, go some bit beyond it. How far? How about h? That distance h. And then you just compute the difference quotient. There's f of x plus h, f of x. And since we're taking the limit as h goes to 0, as long as you've kept, well, hold up, okay, here's the thing, right? This distance is that right there. We've taken the one on the right-hand side to be first. And so this h is, we take the one on the right-hand side first and minus that. That's the run right there, right? So like if that were a 7 and a 2, you would take 7 minus 2, right? Or the right-hand one minus the left-hand one. It turns out that, and let's write that again, okay? It's the limit as h goes to 0 of all of this stuff. The one on the right minus the one on the left over the one on the right minus the one on the left.
Yeah.
And it's the limit as h goes to 0, right?
So it doesn't have to be h. It could be.
And this is what we're about to go into. Just something I want to say. Now, okay. So, is it the same? Is it the same thing? Here's a question I have for you. Is that the same thing as this? The limit as h goes to 0 of f of x minus f of x plus h, x minus x plus h. Is that the same limit?
Yeah. Could you just switch them?
Yeah, I've made both the top and the bottom. You could think about it as I multiply the top by -1, flips it. Multiply the bottom by -1, and it flips it, right? As long as, in one case, I said, okay, go to the right endpoint and plug that in here and here. Then go to the left endpoint and plug it in here and here. As long as you're consistent, you could have said, go to the left endpoint first, and then go to the right endpoint, and it's the same thing.
Yeah.
Okay. Okay. Now, let's do a couple different things. Let's say instead of going to x plus h and using h, let's say instead I'm saying, let's use, I don't know, how about z here. And then this would be, you have your z, you plug in an f of z, and you get that. Now, I want to set up the same difference quotient, and now instead of x plus h, it's just f of z minus f of x. Now in the bottom, as long as we're consistent, as long as whatever shows up here shows up right here,
It's just z minus x.
it would be z minus x. And as long as those match up right there, I'm fine. But now here's the question. I'm going to take the limit as something goes to something else.
As z goes to x.
And, okay, and so maybe I do that. Maybe I do that. I take the limit as z goes to x. And that would equal f what of what?
F prime.
Prime. Oh, look at what I'm doing. I didn't do the prime. It's, yes, f prime of what?
X.
X, because you're fine, because that will compute the slope right there, right? As z gets closer and closer to x, this secant line, the slope of that secant line will get closer and closer to the actual slope you're trying to compute, and it will be at x. Now let's change this up a little bit. Let's say I have the exact same thing, but instead I'm taking the limit as x goes to z.
Then you
Just
just
the limit of z.
Yeah, exactly. So then what this does, x moves this way, f of x moves this way, and then the slope that this will converge to, that secant line will converge to the slope here at this number. And so it'll be the derivative at that number right there, which will be z. Okay? I've given you a bunch of these. Like, it's...
in that one quiz they were all true.
Yeah.
Yeah. Only what I've done in this one, I'm telling you, I give you something like this, and I say, rewrite each expression in terms of the derivative of f. And so what I'm looking for, like he just said, is that this is equal to f prime of what?
Z.
Z. Okay. I've given you a bunch of those. They could be a little tricky, and just imagine if you flipped one of them around or something like that, what could it be? Would it be positive? Would it be negative? Etc., etc. And I'll just say, when in doubt, draw it out. Okay, like you could draw, like I just did, right? Well, you have an x and a z, I guess there's an x and a z, whatever. Okay? And again, f of z minus, let's say f of y over z minus y is exactly the same thing as f of y minus f of z over y minus z, right?
Yeah.
Because if I multiply the top and the bottom by -1, I have not, each by -1, I have not changed this thing at all, right? But if I only multiplied one of them by -1,
That's, yeah, that's,
Then you just flip the top. Or I guess just
or
the
you could
bottom,
just,
yeah.
or whatever, or maybe I gave you it already flipped. Then it would do something to that derivative. And you could figure out what it does to that derivative. Okay. Problem 2 and 3. Really, if you could do these, then you know calculus. As far as I'm concerned, this is the test of whether or not you know calculus. And all of calculus can be summed up, as far as I'm concerned. Rather, okay, so what you do in this one, I'm going to give you a function. And we might as well just do one. So, okay. Let's do something like that. There's your function f of x. X is the input. Now, what I'm saying is, if you could do what I'm about to say, you know calculus. Everything else, like integration by parts, trigonometric substitution, logarithmic differentiation, implicit differentiation, all that stuff are just techniques, really, like of how you go about integrating, or those are just techniques for stuff. And those techniques, you're going to forget them, and you're going to look back at some point, and then you can just get on Wikipedia and be like, wait, how do I do implicit differentiation? Oh, right, okay, I remember. This is, do you know calculus? And what I'm going to ask you to do, I'm going to ask a few questions about this kind of thing. First off, where, again, give it some numbers. Here's 1. And let's say this is 3 here. Here's a question. Where is f continuous? On what interval is f continuous?
0 to 1.
0. And let's assume that it's defined. Let's say that f is defined on -1 up to 4. Okay. So first off, it's continuous on what intervals?
-1 up to 1 soft bracket.
So do I include -1?
No.
No, because there's. Wait.
Because it's soft.
Oh, it's defined there. So yeah, you would.
It's defined there.
But it's
Oh,
not
that's
differentiable, basically.
Yeah, so we're gonna go. And honestly, I wouldn't care, like, because that is one of those questions. Like, endpoints are. If we're taking a class in topology, this would be a different matter. I really don't care about the endpoints. But yes, okay. So we'll include 1, and we're going up to where?
1.
Okay.
Soft.
Soft bracket.
Yeah.
Then 1 to 3.
No, 1 to 4.
No. It's
So
not.
I'm asking where it's continuous.
1 to 4 with hard brackets.
Yeah.
So both hard brackets.
Well,
4 would be soft. Well,
Wait.
yeah, it would be hard. I think.
Well, if we're going to
If
call
we
that
got-
one hard, then this is going to be hard. But what about the 1?
Yeah, that's hard bracket.
yeah.
'Cause it's defined there.
Well, it's not continuous.
It's not continuous at 1. Remember, the definition of continuous is that the limit has to exist from both sides. And so that's why I said this is. It's like, well, does the limit exist from this side? Does the limit exist from this side?
We don't know.
Well, I mean, technically, if the domain ends here, if there's nothing more after 4, then it's continuous at 4, because both sides doesn't have any meaning over here. There's nothing over here as far as f is concerned. It's not defined there. So it's one of those, you could do this either way and I wouldn't care. Like, this is, again, a technicality that that we're not interested in for this class, okay? Like, it's like, well, technically, both sides, in this case, well, it's on its domain. So its domain doesn't exist past 4. So the limit exists in its domain. Here, this is in its domain, this is in its domain, and they're going to different places from both sides. So the limit from both sides does not exist. That's why it's not continuous there.
Okay.
Does that make sense? Okay. Again, I don't care about the endpoints. You can include them or not. Yeah. I'm sorry. These endpoints, like on the domain of definition.
Yeah.
Okay. And so, just to be clear, I'm saying that the domain of f is equal to, and it is defined here because we have that.
Yeah.
So it is defined everywhere from -1 up to 4. I have you're going to see a picture like this. I don't have the dots. You don't need. As you'll see, you don't need a dot to know that it's not continuous there, do you?
No.
Look at it. It's called a jump discontinuity. It's obviously not continuous there.
Yeah.
Okay? All right. Okay. So again, I don't care about the endpoints. That is I think technically, in this topology, in the topology of the real number line, it's continuous there. because its domain is there. There's nothing, as far as f is concerned, there's nothing out here or back here. That is all of the domain. And so, again, I don't care, that's not the point. I just want you to be able to go, it's not continuous there, but it is continuous there. That's the real, that's what you need to take from calculus. Like, it's continuous there, okay? Now, where is it differentiable?
Everywhere except that 1 and 3.
Yeah, so we'll say from -1 up to where? 1.
Soft bracket.
Yep.
Union 1 to 3.
1 to 3.
Soft brackets. Union 3 to 4. Soft part.
There we go, right? Because you could take a derivative everywhere else. Now here's a question though. It looks like, to me, and the way I drew this is that it goes to 0, the slope goes to 0 here, and then down here it looks like the slope is also 0. So the derivative would match up from either side. If you were taking, right, if x were over here, and you were taking the limit as x goes to 1 of f of 1 minus f of x over 1 minus x. Notice I flipped them around, right? We would normally do it like this as x goes to what? Well, I guess either way, it's exactly the same thing. That's the exact same thing, like we just talked about. It doesn't matter which way. At any rate, as you compute this, you would find my limit's going to 0, right?
Yeah.
If you put your x over here and did the same thing, you would say my limit's going to 0, right? Because as you compute this slope, you go, yep, going to 0, going to 0. They match up. And you might be tempted to say, well, then, if the limits agree from both sides, then it's differentiable. But technically, that's not true. Even if they are going to the same place, technically, you cannot be discontinuous and have a derivative there. Just by definition, f has to be continuous for the derivative to exist. Okay?
Yeah.
It's just definitionally. You cannot be discontinuous and have a derivative. Even though the derivatives both go to the same place as you go, technically, it is not differentiable there because there's a discontinuity. Everybody with me? Now, it's not differentiable at 3, well, obviously, because the limit from this side goes to +1, the limit from this side goes to, I guess, -1, the limits don't agree, and so no, you're not good. Even though it's continuous there, it's not differentiable there, so we have to pull that point out. Okay? Where is this function integrable? We didn't really talk about this, and that's why I'm bringing it up right now. Where can you take an integral of this? And now we're going to think about the integral as just the area between the curve and the x-axis.
So you could from -1 to 1.
Yeah, you could certainly do that. You could take the integral here, and then from here, and you would find that it's this right there, and then this right there. Can you integrate here?
Yeah, you can. I think you just can everywhere. Well, except you can't.
You just have to
have
split
to
it
break
up
it at
into
the
multiple.
continuity. Yeah.
So you could take. So what are you telling me that it's integrable on what interval?
-1 to 1.
-1 to 1.
Soft brackets. Or I guess.
No,
Well, you can't do it. You can do it there. You just can't do it
yeah,
with
it
the
just
other
has to
one.
be-
You can do it there. It's perfectly well defined. Now,
You just can't do it with the other one.
Yeah, it wouldn't have to be multiple.
you could integrate over jump discontinuities.
But you have to split up the integral, right?
Well, in practice, yeah. Well, in practice, what this would look like. Let's say we're integrating from -1 to 3. Yeah, let's say we're integrating from -1 to 3. f of x. In practice, you would say, well, that's the same thing as the integral from -1 to 1 plus the integral from 1 to 3. And that's how you would calculate it. But this is equal to that.
Yeah. Okay.
So there's no problem with a discontinuity right there.
Okay.
You can integrate over it, and it is and it's equal to doing them by pieces. The integral's a linear operator,
Yeah.
right? So this is that, perfectly fine, because the function is a. You would say that f would be a piecewise function. You would say, well, f of x is then, I guess this is some kind of like, I don't know, a minus x squared minus 2 or something like that on x is between -1 and 1. And then maybe this is some kind of sine or something. Yeah, we'll say it's like sine x when x is between -1 and 3. Oh, that's whatever sine of some kx from -1 or from +1 up to 3. We'd have to do that. So it's not defined. Yeah, it's defined there, not defined up at when x equals 1. It's no longer that. It's now that. When x is equal to 1, it gives you that guy. And then it does something else, right? And whatever. And that's a perfectly fine function to integrate, because you could just integrate the first part, integrate the second part. So in practice, given a function like this, in practice you would say the integral from 1 to 3 is these guys, and you'd break them up. So that you'd say, okay, it's 5 minus x minus 2 squared on that interval, and then over here it's sine kx on that interval. But when you add them together, you get the area that you're looking for. That's what the integral is. It's the area that you're looking for. Now, in order to prove all the stuff that we did about the integral, we said that it had to be continuous on the integral. That's just to prove it the way that we proved it. Turns out that if you have a countable number, that means it could be infinite. You could have a jump at every integer, let's say. And as long, and you could, your f could go out to infinity, right? So maybe something like this. Right, so f of x is 1 over the floor of x, which is the lowest integer. So when it's between 1 and -1, it would be 0, so it's not defined there. From 1 to 2, root x, or I'm sorry, floor x is just 1. So floor of 1.1 is 1. Floor of 1.9, still 1. Floor of 2, now it jumps up to 2. You can integrate this guy, right? It's perfectly, like, it would be a Riemann sum, or I mean, it would be a infinite sum. It actually, it doesn't converge. But if you do this, then it would converge. Right, because that would be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and we could actually figure out what that is. Convergence to an actual value. And so, everything that we talked about with integrals works if you have infinitely many discontinuities. It's fine. It's just, you can't prove what we proved about that being about the integral. And this is what I mean when I said what we proved from some number to x, that the integral of a derivative is the antiderivative of the thing, right? The fundamental theorem of calculus. right? Is that the fundamental theorem of calculus?
Yes.
Yes. Okay. Good. I'm glad you guys got that out of this class. The fundamental theorem of calculus. In order to prove it, we had to assume that this function was continuous. It turns out that if it's not continuous and it has a bunch of jump discontinuities, it's still true. It's just harder to prove. And so, I want you to know going forward that just because something has a jump discontinuity doesn't mean you can't integrate over it. And the result will be a continuous function. We're going to get into that in just a second.
It wouldn't just be a thousand.
Hold up. Good question. Okay, but everybody got this, right? So, and that's not really, like I said, if you got this, you got all calculus. Well, no, this is just, this right here is just kind of some technicalities that it's really good to remember, okay? And honestly, after I took calculus, I dropped all this. I forgot all that for a long time. Then when I got into analysis, I was like, I should have really put that in my head. So, this is important stuff if you're moving on. But this is what calculus is all about. This right here. Given f. Draw the derivative of this guy. Now, we want f prime of x. And I say, in the thing, in the exam, I write, in fact, I'm gonna read exactly what I wrote about this. Oh, don't lock me out. It locked me out. It's because I talk too long. Okay. I say your graphs only have to be qualitatively accurate. You do not need to explicitly measure anything that's not obvious. What I mean by that, like if it's obvious that that slope is -1, then do that. If it's not, or if you can't quite tell what this point is and what this point is, because it's between 1 and 2, and this one's between 2 and 3, it doesn't look like it's exactly in the middle. I don't care. That's not the point. We don't need to measure stuff. But I want it to be qualitatively accurate. So let's draw a qualitatively accurate one of these, and let's just agree right now that this thing looks like it's going to 0 right here. Yeah. Looks like it's going to 0 both ways there. Okay, so it's derivative. Now, it's not differentiable there. You already told me it's not differentiable here, and it's not differentiable here. So we better have holes in the graph of this thing. Okay. All right. Let's start with some points that we know. And it looks like I said, that looks like a 0. So let's go ahead and say that here it's 0, but it's not defined there. So I'm going to go ahead and do a hole right here. Okay. Now, let's work our way back.
It goes to negative infinity.
Now look, hold up.
Positive.
Oh, positive.
The slope is positive, isn't it? Yeah, careful with that, right? So it's going from 0, getting more and more positive and more positive.
Yeah.
And I mean, yeah, okay, we'll say that there's like an asymptote here. Maybe it looks like that. So if the slope is getting more and more positive as we go back, then it should cup up, right? It should be cup up. Okay? And so, and another thing, as you're doing these, think about, like that kind of looks, maybe it looks like a parabola. And so the derivative of a parabola kind of looks like a line, right?
Yeah.
And so, now, given that you said it keeps going and keeps, like that's how you read this. Like you said, this doesn't look like a parabola here. You said it looks like it's going to go down to negative infinity. Okay, then this had better go up to, I'm sorry, this looks like the slope is going up to infinity as we keep going. Well, then make that keep going up, right? And so it should curve up. If something's obviously a parabola, right, or like, if you're, well, it doesn't really matter, but if it's like, if my thing looks like that, then its derivative should look like some kind of line, right? And it would have a negative slope and then go to 0 and then have a positive slope. So its derivative would look something like this.
Yeah.
Yeah, more or less. Maybe it's still curvy, who cares? Again, qualitatively accurate. Let's try to make it look good. Okay, so over here, what happens? It's at 0 and then what happens?
Gets more negative.
It gets more negative.
But then it
And it
goes back to
continue,
0.
then it gets less negative, and then right about here, which let's just put a point right there,
Two,
like
I
that.
guess.
Yeah, we'll call it 2. There you go. We'll estimate that that's 2. We'll say this bit right there is 2, and so this bit right here is 2.
So it's like goes down.
So it's it starts getting more negative, and then it gets
down to
down
back
to
to
here, and then it gets less negative until it gets back to 0 here at 2. So here should be where it gets the most negative, and so something like that,
Yeah.
right? Okay. Now we're here, and it's going to start getting positive again, and it looks like it gets more and more positive until it looks
It
like
just stops, I
it-
guess.
it hits some constant value right there,
Yeah.
right? So maybe here is where it hits its constant value. So here is where it hits its constant value. So it starts ramping up and then hits a constant value here. Starts ramping up and hits a constant value there. Now it's just a constant value. The slope is constant until it gets to 3. So the slope is constant until it gets to 3. Now, there were no bends here, so this should be kind of rounded off. Nice and curvy. Okay?
And then it jumps to negative.
Then it jumps to negative, and it looks like it's symmetric over here. So I'm going to try to make it symmetric over here and say, okay, now, does its derivative exist there?
No.
No,
So,
it's a dot.
I should put a hole, and then it's going to jump to, and again, it may or may not, like if it did something like this, and then way down, then I'd say, okay, it's way steeper here, so it's going to go way down to a steep, or a more negative slope. Here it looks like about the same, so I'm going to say, okay, whatever it was up, now it's just become negative, and so it's negative here. And is the slope constant?
Yeah.
So in that case, I would do this. There you go. Okay. Okay. Here's the hard part.
Draw the derivative of that.
No.
Oh.
No, actually, I mean, yes, but then
Oh.
again, if you could do that with this, you could do that with this.
Let's do it the opposite way.
The opposite way.
Yeah.
That's
And
the
so
derivative.
the antiderivative. And remember, the antiderivative can be shifted up or down or whatever. Or we could define f of x to be the integral of little f of t dt as t goes from some number up to, say, x.
Okay, yeah.
Right? And in this case, I'm going to say, let's let that lower bound be -1. And that's the function we want to draw right now.
So
So, here's a question.
it starts with negative slope. Or
Wait a second. Yeah, the slope is negative to begin with. But what's the value of blue f when x is equal to -1?
wait,
So I'm asking you,
from
what is the integral
Zero.
from -1 to -1 of any function is 0?
Yeah.
So it should start at 0. And this is right, because you have the antiderivative of a function. It's gonna, the antiderivative is gonna look like something. And the only question is, how high up or down is it shifted? Which could also be a way of saying, where are you putting your 0? Well, here we're going to put our 0 right there. So we have some f that does this. This is what we find that capital F looks like. Now, shifting it up or down is the same thing as saying, make this part right here the 0. Bring him down to 0.
Yeah.
Which, if you think about the fundamental theorem of calculus, that's the same thing as the antiderivative of f at x minus the antiderivative of f at -1 minus off whatever the value is there, brings him down to there.
Yeah.
Yeah? Yeah. Okay, so that's all equivalent. We could just say the integral, I could have written it this way, f of x is just the antiderivative of f of t dt, which you would say is the antiderivative of this plus some constant.
Yeah.
Right?
And we're
Or
just
I guess the
gonna
t, I guess this would be x, sorry. Plus some constant. That constant is determined by that,
Yeah.
that guy right there. And so you're basically asking which point along here are you going to drag down to 0? That's the point we're going to drag down to 0 right there.
That makes sense.
Good, I'm glad. I hadn't practiced this little spiel. I'm glad that makes sense. Okay, good. So, okay, we know that capital F starts here. Then its slope is negative, and it's getting less negative, right? It's
How
getting, so it's starting off negative, it gets less negative, and then here at, let's call that negative 0.5. Can you read that? Can viewers at home read that?
It's at 0.
Yeah, and then at 0.5 it comes, the slope, we'll just do it in black. Ugh. This is at negative 0.5, we'll say. So at negative 0.5, that's where the slope goes to 0. So that means this thing needs to have, it needs to come down, and then its slope is 0. Now its slope is positive, and it's getting more and more positive, and it's hard to tell just by looking at this whether or not it comes back up through. And this is what I'm saying, you don't need to measure, okay? Like, if you could tell that this area was exactly that area, then you could say that this comes exactly back up to here. Can't really tell there.
Yeah.
So I'm not going to worry about it. In fact, I'm going to go ahead and just pretend that there's not much area down here, just so we can see what would happen. And say there's way more area here. So he gets positive, he's going to keep getting positive and positive and positive until he reaches some point here at 1. And so he keeps getting more and more positive 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 until we get to 1.
Yeah.
Okay? Notice, oh, I drew it as a line. I don't care. Right? It should probably be more curvy. It should probably curve all the way up.
Wait, but doesn't it? Oh, yeah, okay. Yeah.
Yeah. Yeah. That's what I'm saying. If you can do this, you know calculus. Now what happens?
Changes, so it's not negative, but it's less positive. But just, there's no curve.
It doesn't matter. Yeah. And so now think about this, right? We started with 0 area. And then as we moved this way, that's what this says to do, right? When x is here, we're computing this little bit of area. It did not jump, did it?
No.
Because you start when x is -1, you have no area, but then when it's really infinitely thin, you don't automatically jump, right? It's continuous here,
Yeah.
right? It continuously gets more and more negative because of that. Okay, as you're adding up that negative area, you're getting more of it, more negative area, right? So, same thing happens here. We have some amount of area that we've added up. And it looks like we've added up enough. Now this bit has outweighed the other bit, okay? But now, as we start going, we're adding up. Now we're not adding up as much area, but we're still adding area.
Yeah.
Okay, just not quite as fast as we were here. So I'm going to show it.
It's just gonna jump. Like there's gonna be a corner, but it's
Yeah.
still gonna be positive.
Yeah, exactly. He's not, yeah. So his derivative, this is the derivative of this. The slope is some positive number. The slope is still some positive number, but just not quite as positive. And then he's getting smaller and smaller until he gets to 2, where, I'm sorry. And he gets smaller until he gets to, let's call this 1.5. 1.5, where the slope is 0. Okay, so big slope, jumps to a smaller slope, and then goes to 0 at 1.5. So, let's do it like this. Corner this way, and then something like that. At 1.5, now his slope is 0. Then he gets negative, and gets most negative when he gets down to 2. Then he gets less negative until he gets to here, which we'll call this 2.5. 2.5 to where the slope is 0 again. So he's negative. So I'm just thinking about this. We're here. He gets negative, gets most negative at 2, and then gets less negative until we get to 2.5. So negative, most negative, less negative back. So it should be some kind of S type thing, like that. So that's from 1.5, most negative here, and then nothing here. So most negative, less negative, boom. 0 here at 2.5. So like that. Now he's positive, and it looks like a line. So the antiderivative of a line is a
Parabola.
parabola. So this should look like a parabola going up
Okay.
until we get to 3. So he's a parabola from here to say here. Parabola.
Yeah.
And then now it's negative, so it's a negative parabola. So we go up to 3, and then
The slope's still positive.
slope is now negative. Wait.
No, it's the slope's
The
still-
slope?
Yeah, this.
Yes, the slope. Oh boy, man. See. All of calculus right here. All of calculus is right here. The slope is still positive. So he's changing direction. So now he's concave down. This would be an inflection point, right? Went up, and now the cup comes down until we get to here where it's 0. And we'll call that 3.5.
So it's gonna start.
3.5. So he's gonna
Just
also a cup, right? A parabola. So another parabola that goes like that at 3.5.
Yeah.
Inflection point right there because we've changed there.
And then
Because its second derivative is positive here. Its second derivative is negative here.
oh yes, yeah.
So the second derivative of this, so concave up,
Yeah.
concave down. Yeah, man, this is all of calculus right here. Okay, So then at 3.5 is 0, and then it looks like
Goes negative.
goes
Another
negative.
parabola. Or I guess it's the same parabola.
It is the same, yeah, it is the same parabola. So this thing is that guy right there. And then that's where he ends. Alright? That's all of calculus. If you can do those things, you know enough calculus to... Now, I mean, you could use this to inform this about concavity to really make this good, right? Like, from 1 to 2, second derivative is negative, so he's concave down here. It doesn't look like I made that concave down there. I should make the whole thing concave down from 1 to 2. And then at 2 is where he's concave up. So we have our max here at 1.5, and he should be concave down the whole time. Yeah? I would suggest you do that. You don't do the one you're going to turn into me.
It doesn't have to jump there. It can't be all smooth. The original one at 1. It has to like jump to a lower, to a less positive slope.
Oh, at 1. Yes. I'm sorry. You're absolutely right. It should. Yes. Thank you. Right here should not be smooth. And so what I would probably do is, as I'm going back with this, I would exaggerate this and make it like that. So please don't turn into me your first draft. Okay? Concave up, concave down, and a corner right there. You could exaggerate the corner like I just did, right? Like here, I've like put them way up, like you know what I'm saying, right? So please, if you use all three, and you should do it in this order. Given this, get this guy first, then go back and get this guy, because this guy gives you concavity with him. Okay? That's all of calculus right there. Questions before we move on? And again, like this isn't like I say this is all of calculus. It's like, well, integration by parts isn't on here. Right, but those are techniques, right? And that's stuff that you'll remember and blah, blah, blah. This is the big idea right here. Functions and functions which are, given a function, have a new function which tells you the slope of the original function. That's the big idea. And then if you do that in both directions, what does that do? How does that relate? Whew. Tough stuff. Okay.
And yeah, I gave you something like that. Good luck. It's yeah.
Implicit differentiation. I already mentioned that. Oh man. Problems 6 and 7 are so cool. Problem 6 and 7. I love problem 6 and 7. I hope you guys. I don't want to say anything about them. Later on in the extra credit, there's 3 extra credit problems. Later on, I mentioned something about problem 6 and 7. But I think you're really going to enjoy them. Both of them I wanted to do this year, and we didn't have time. I was like, I'm just gonna make you do. And so they are so cool. I hope you enjoy them. One thing I will say, a few things. Problem 6 says, suppose a function f has the properties that, for any real numbers x and y, we have stuff. I say, find f prime by using the definition of the derivative. So I say find f prime means you should write f prime of x equals, and then I say the definition of the derivative, which is
limit as h goes to 0 of f of x plus h minus f of x over h.
That's the one you should use. There's a bunch of different ways of doing it. That's the one you should use for this one. And you'll notice that one of those properties I gave you can be directly used, bam, right there. From that, There's a lot of this. The next one is a lot like this too. I say use the definition of the derivative, and then use the properties. And the idea is like, let's do it this way. Let's say you end up with some expression. And let's forget about functions and everything right now. Let's forget about functions, and let's just say we have something like this. Yeah. Wait. Yeah. No. Yeah. No. This actually what everything I just did right here really doesn't have anything to do with this. Let's say you're looking at that and you're like, man, I don't know what to do with that. What might you do? What's your intuition telling you to do?
Split it up. Right.
You could split it up. What about, are there any like terms here?
There's a y in the 5 and 10.
Okay, so maybe,
So factor out.
let's
Put the y ones together.
in other words, group like terms.
Yeah.
Group like terms, right? They say, hey, this has a y in it and that has a y in it. I have no idea what, and look, I did not tell you what the goal of this was. I didn't say, we're trying to, I didn't say anything. I just said, like, what do you want to do with this? I said, well, there's y's, I don't know. Put the y's together, then what? And you were saying you could, yeah, why not pull out a 5y? And you have an x minus 2 left over. What do you want to do with that?
Could split it up.
You could split it up. Okay, so you have 5y x minus 2 plus 2z, and you're saying split up like that?
Yeah.
Right. Yeah. That's just what you do. Why? I don't know what the goal of any of this is. And when I tell you use this, and then the property, and you're gonna plug some stuff in it, and you're gonna go, I don't know what to do. Play around with it. Just play around with it. And this is what I mean. Just I don't know. Those things go together, and these things they go together. And okay. And, well, now what? I don't know. Oh, and that's what's gonna happen. Okay. Ditto with problem 7. Like you might look at, I have no idea what to do with that. I don't have group-like terms. And then maybe something happens when you do that, and you. I gave you. I gave you that. That's what's going to happen with this, and that's what happens in mathematics. Like sometimes you don't know what you're trying to do. You don't know what something's going to do when you plug something into something, and so you just play with it, and you play with it, and you play with it, and then hey, look at that. That's what's going to happen with this. And the result is going to be so cool. It's going to be so cool. You're going to love it. Did I say, okay, so find f prime by using the definition of the derivative, the aforementioned properties. Yes, I typed in aforementioned. The aforementioned properties and L'Hopital's rule. And L'Hopital's rule, okay? So in order to use L'Hopital's rule, let's just think about this. Limit as, let's just say, x goes to something a of something. If I want to use L'Hopital's rule, this has to go to something. There's two possibilities. Either 0 over 0 or
Infinity over infinity.
and a plus or minus doesn't matter, right? If I say use L'Hopital's rule, you better justify it by saying, hey look, the limit of this thing, so let's say you have some f of x over x minus a, right? as x goes to a.
Yeah.
Like, don't just blindly use L'Hopital's rule. If you're about to use L'Hopital's rule, tell me, like, oh look, this goes to 0 over 0. Thus, or you know, what I've done is then I go L'Hopital. This is the same thing as f prime, the limit f prime, x goes to a over, what's the derivative of that with respect to x?
1.
Yes, 1. There you go, right? And then you say, okay, and then that's the same thing as f prime, I guess, of, are we going to, oh, we're going to a, right?
Yeah.
So that would be the f prime of a, right? It's just L'Hopital's, right? Like, I'm not saying anything new or anything. Just saying, use L'Hopital's rule. Right? That's what I mean by it. Notice that, oh, you could use it somewhere. And so justify it, then use it.
Yeah.
And then magic happens, and it's so cool. And you're going to go, no way. Really? That's cool. The second one, I tell you, okay, and then there's more to do with problem 6, because but when that happens, you're gonna go, okay, well, actually you might go, oh man, right then and there, but it might not be until you do the other things I tell you to do. So problem 7, say suppose there are two functions f and g which have the following properties for all real numbers x and y. I give you the properties. And then I say, using only these properties, do something.
Okay.
I guess I didn't say explicitly, find f prime by using the definition. But if you see how these, like, you'll look at them and go, oh, you're asking me to do the same thing. Find the derivative by using the definition of the derivative and the properties. I didn't say it, but that's what you do, okay? Okay. Problem 6 and 7, really cool. Really cool. Here's another thing. I wanted to say this at the beginning, I forgot about this. Suppose that you have the limit. Yeah, let's do this. As x goes to a of f of a over x minus a. So let's make this easy. Let's just make it much easier. Oh, f of a. Sorry, that should have been an x. Let's just jump to the chase here. Let's say you have a limit like this, and this equals, and I tell you, there's this limit, and I'm telling you, it is equal to some number.
Okay. Wait.
I'm telling you that it's equal to some number, some finite number. Let's say 5.
So then f of x.
What does that tell you about f of 0?
That has to equal 0.
It has to, thank you. It has to equal 0. Because if it didn't, if f of 0 was any other number than 0,
Then it just blows up.
then, like, let's say, exactly, right? Then you'd say if f of 0 was, say, 3, then this would be the same thing as a 3 over 0 equals a 5. That never happened, right?
Yeah.
The only possibility, if this is the case, the only possibility is that this thing must be 0. Okay? Let's play around a little bit more. And let's say that actually let's do the same one. When I tell you that it equals 0. What does that tell you about f of 0?
It also has to equal 0.
Yeah, there's no difference.
Yeah.
Right? That's a finite number. That's not infinity. The only way you could get this, you could plug something in here and get something finite. The only way you could do that is if that's 0. And even then, sometimes that doesn't work, right?
Yeah.
Right? Because it depends on how fast you're going to 0, like, you know, log x over x. This guy goes to 0 way faster, so this limit, oh wait, x plus 1. There you go. This limit as x goes to 0. Both of them go to 0,
Yeah.
but this one goes way faster.
So then it's
And so in this
just
case,
0.
it's, well, hold up. Let's just, because this would be a great practice for L'Hopital's rule. Let's say that I have the limit as x goes to 0 of log x plus 1 over x. This goes to what over what?
0
1
over 0.
over
How about log 1 over 0? Log 1 is,
0.
Yeah, 0, 0, 0.
so can we use L'Hopital's rule?
Yes.
Yeah, so let's use L'Hopital's rule. L'Hopital means that this is the same thing as the limit as x goes to 0 of
1
1 over x plus 1.
over 1,
over 1.
Yeah.
Oh, this one actually did work out.
which is just x
Which
plus
is-
1.
Just plug in a 0,
Yeah.
1 over 1 over 1 is just 1. Okay, so I guess this one does work out. Whatever, okay, who cares? But notice that he also had to go to 0 for that to work out.
Yeah.
Yeah. Okay, so I guess they go to 0 at this rate. Oh yeah, because the slope of him here is 1.
Oh, it is?
Yeah. X
Oh, I
plus,
guess, yeah.
x plus 1. And so when you shift him over, right, log of x plus 1, this is log of x plus 1. And he's going to 0 at the same rate as x.
Yeah.
But if we did this, there we go. That's what I'm looking for.
Okay, then it just doesn't work.
It does not work, right? Because you still get this, right? They're both going to 0. And then by L'Hopital's rule, you have 1 over x plus 1. This is 2x. Then this goes to plug in a 0, plug in a 0,
That's just blows up.
blows up. Okay? So just because you have this doesn't mean, right? But if you do get a finite number, if you do get any finite number, let's say pi, then you can conclude that f of 0 is equal to 0. Right?
So 0 divided by 0 equals pi.
It might. You could find one that does that. In fact, how about pi x over x, the limit as x goes to 0
Yeah.
is equal to pi. So yeah, 0 divided by 0 can equal pi. Right? Okay. Also, let's do this. The limit as x goes to a of, how about this? 3 minus f of x and x minus a. I tell you that this is equal to some finite number. Maybe pi over 4. Any finite number. It's finite. What does that mean?
3
F of
minus
x
f
is
of
3.
Yeah, f of x.
F of x equals 3.
F of what equals 3?
X.
X.
F of
F of
x is a
a,
function.
F of-
Aha! F of a must be 3
Yeah.
because, right, as this goes to a, 3 minus f of a must be 0 in order for this to not blow up, right? I wanted to, like, I remember when we were doing this, I made note that, oh, I didn't go into this explicitly, but it's so obvious that, I mean, it has to be the case. In fact, it might have been in the homework problem. Not sure. And let's see, what else do we got? Okay. And I didn't tell you, yeah, okay. When everything we just talked about just now, like I say, like I can tell you, look, you could deduce that from these two limits. You could figure out what these are. So it should come as no surprise. Okay, find and classify all extrema. Recall that to classify. So extrema are the extreme values. The extrema of a function occur when f prime of x is equal to
0.
That's what we mean. That's what extrema are, right? Whenever this derivative is equal to, I tried to make that one of these. Right? Whenever the derivative is equal to 0, you get an extremum. Okay? And it might be the case
It doesn't quite.
that an extremum is not extreme, right? What do we call those?
A local for maximum or minimum. Wait,
So wait, what's this one called? So extrema, that's a
local maximum.
local max, this is a local min, and that's a,
Uh, wait,
No.
it's a local min, right?
That's a, wasn't the other one an absolute?
I put inflection point. It should be saddle point.
Oh, it isn't because it changes.
I can fix that
concave.
right now. Hold on, let me fix that. It's called a saddle point.
But doesn't
I don't
it-
care, but you better be able to tell me what it is.
Well,
Okay.
it isn't. It changes concavity there, right?
It changes concave.
Which
Or
is
does it?
I think. It,
Oh, well, yeah. So that is the crux of the issue, is that the derivative 0, but it is saddle point. Okay, it's called saddle point because it looks like a saddle. Let's look at y equals x cubed.
okay.
Concave up, concave down. That's the crux. It is here, its derivative, y prime, 3x squared, at 0, y prime of 0 is 0. So that's an extremum.
Yeah.
But to classify it, we would need to take the second derivative and get 6x. Plug it in. And we get a 0 up. It's the test for max or min is inconclusive. That means it's a saddle point.
Okay.
Okay, that's how you classify them, right?
So
Now,
a saddle point is just it has derivative of 0, but it's not a min or max.
right. Its derivative is 0, but it's neither a min or a max. And it looks like a saddle, because if you imagine that you're riding on a horse. That's your horse.
Do we have to draw this?
You better. Okay, right. That's or a duck, a spider duck. If you're riding on a spider duck, that's what it would look like if you had a saddle on a spider duck. So, okay. So just remember that. Now, just a few more points here. There's so many questions on this. Oh man. Okay. So yeah, classify all extrema for the following function f. Recall that to classify is to tell whether a function has a maximum, a minimum, or a saddle point. Okay. I'm glad I saw this because I didn't want to say this. A right circular cone is this thing. It has a circle. And it's not, it comes straight up, right? It has two properties, or it has two parameters that define it. Its radius, r, and its height, h. Okay?
The surface area.
You're gonna have to do a bunch of stuff with this cone. There's a lot of stuff to be done with this cone. But let's imagine that we're looking at it flat. If you're looking at it flat, it would look like this. There's a bunch of ways you could orient this thing if you need to, I don't know, find some of its properties. One of the ways you could orient it is this way. And in that case, you could put axes anywhere. You can put axes here if you're so inclined. I don't know why you would. There are better places to place your axes. And you don't have to orient it this way. You could also orient it this way. And you could put axes anywhere. Anywhere on the page that you want to put the axes. There's a bunch of different ways of putting axes on things, okay? And so that would be like its projection of this thing on the... And I'm just noticing this thing, just let's forget about this for a second. What type of function is this?
Line.
It's a line, so it has the form what?
Line x plus x, and x plus b.
That's in general, that's what it is, right? And you would need to know, in order to find m, you would need two values. You would need to know what this value is from here to here, and you would need to know what this value is from here to here, right?
Yeah.
You would need the rise
Okay.
over the run.
Yeah. It goes through zeros. You don't need.
Okay. All right. Just making sure that we all are on the same page, because that would make your life much easier. There's a lot of ways of doing what I'm asking you to do. A lot of ways you could orient one of these right circular cones. And I do say, okay, that our right circular cone that we're going to be doing stuff, I say is empty. And what I mean by that is that this part does not exist. It's you could ignore this thing right here like that. It's not like in the case of, you know, like a box. If I say a box is empty, then that means there's no lid on it, right?
Okay.
And so you can think about this as being a cone without a lid. It's empty. You could put stuff in there.
Yeah.
Okay?
Like an ice cream.
Huh?
Like an ice cream cone. Is the question about ice cream?
Maybe there's lots of questions
much
about
ice
ice cream
cream?
cones.
How much ice cream can you fit?
Look at what I wrote here. I'm cracking myself up with this. I think it's hilarious. Differential equations. Have fun with that. I mean, it's really straightforward here. You're going to solve a differential equation. Do not make it too hard. Do not make it too hard. Don't make it too hard. Because, you know, here's the thing. If you have dy dx of any function of x, what do you need to do to solve that? To get y by itself? Just integrate it, right? I mean, because all this means is y prime is f of x. And you just integrate it. Or if you really need to, dy, because I even say it's separable.
Yeah.
Like, find a separable differential equation. Well, this is separable, isn't it? And then you just integrate the guy. Don't make it too hard. You know, there's no crazy stuff you're going to need to do. Okay. All right. I tell you, give an exact answer. Problem 11, give an exact answer. Then plug it into a calculator to report an approximate answer. So, a rectangle is entirely defined by two parameters. Its width and its length. So if we somehow found an optimal rectangle, if I said something like, what dimensions optimize this rectangle, I'm looking for some L which equals, say, square root of 2, and some W. Those are the dimensions which optimize said rectangle,
Yeah.
right? And they entirely determine the rectangle that we care about.
Wouldn't they just be equal?
Huh?
Wouldn't it just be when L equals W?
Well, yeah, that's what it would. Well, what am I optimizing? I didn't tell you. If we're optimizing area, yeah, that's when L equals W. But if this thing, whatever, just you get the idea, right? It depends. But let's just say we found that the optimal thing, because maybe this is constrained by something, right? Maybe I'm making a piece of paper and it has to have certain properties, right? It can't be equal. And so, given those properties, we have some function that we optimize, and then we find that the thing that you want has this. So I say, give an exact answer. That's what I'm looking for, only it's not L and W. And then approximate it. So then you would say, okay, L is approximately 1.41, whatever it happens to be. And I would carry about 4 decimal places there. I don't remember what this is. Let's just say it's 5. And
So
then...
you don't want us to just write what it is, you want us to actually evaluate.
Yes, because it's going to come up later. So in problem 11, I tell you, give me an exact answer. So you give me an exact answer, okay? And it's going to be ugly too, but you're going to give me the exact answer. Then plug it into a calculator and give me approximate answers. So I think this is bigger than 2. So this is 2 point something. Let's say 1, 2, 8. I don't know. And so then, okay, 1, 2, 8, 7. Because 4 decimal places will be great for what you're about to do. Okay? And so I want both there, the dimensions that optimize the object. Those are the dimensions that optimize the object in exact form, and then approximated with decimals. And then you're going to do a bunch of other stuff, and then you're going to use these later on. So, fair warning. Okay. You're going to do one thing on the Laplace transform. I know you didn't give me any homework on it. Mika's like, yeah, you can't give him stuff yet. Give him homework. They should have homework. Well, no. The only thing I'm telling you, I'll just tell you what it is. Okay. So recall that the Laplace transform of a nice function f is this. STF t dt. Like that. Yeah?
Yeah.
And I say find the Laplace transform of sine. So in other words, you are to find the Laplace transform of sine t, which is the interval from 0 to infinity e to the minus st sine t dt. And the thing is, like, I'm only bringing this up because I mean that's all I'm asking you to do. And the thing is, you might be you might think, oh, I remember what he said about the Laplace transform. He said there's a table for it. And so you have, and I remember he wrote down this table, and 1 went over to, what was it? 1 over s. And e to the at went over to 1 over s minus a. And so on. And then we got to sine at went over to, I think it was a s squared plus a squared. And then we had cosine at s squared plus a squared. Something like that. And then you go, oh, and I remember, he said that you just use the table. Right, but all of this side of the table had to be calculated by some human being. That's what you're doing right now. You're going to confirm that this gives you that in the special case where a equals 1.
Oh, okay.
Because
So
the A is a bit more complicated.
So just, we're proving the table, basically.
You're just, this is what I want you to do is get a sense of how would you create such a table? Well, you'd have to go through and do all these with all these little bits of functions, right? Because what you do is you take the Laplace of your differential equation and you get some function of s that is, terrible. It looks horrible. You have like s times 2s squared plus 3 over s minus 1, s squared plus 1, s squared minus 5. And then you say, now I have to get that back. And so what you do is you break it up into little bits, and hopefully one of those bits matches one of these bits, right? Like hopefully you get something that looks like this, s minus 1 plus 2s, s squared plus 1. And then you get a I don't know, 5 over s squared minus 5. And then you look it up, and you say, because the Laplace transform is an integral transform, that is that, that is that, it just has a 2 in front of it,
Yeah.
right, and so on and so forth. But in order to get this nifty, handy information, somebody had, at some point, had to do this. That's what I want you to do.
Okay.
The special case, and I'm not going to give you sine of AT, because that's rude. That's very rude. I'm just going to give you sine of T, and it should be, what should it be? If sine of AT is A over S squared plus A squared, what would sine T get transformed into?
It's 1 over s squared plus 1.
It should be. That's what you should get. Okay? And all of these, please, use everything at your disposal. Use Desmos. Use Wolfram Alpha. I want to see your work.
Yeah.
Right? But, like, that would be a great way of doing this, right? Okay, then the extra credit problems. I stayed up to 2 a.m. last night. I was like, you know what? I'll do the extra credit problems after class, because I didn't have them done. I worked on this all day yesterday. And I was like, okay, the extra credit problems aren't done. I'll do it, you know, either in the morning or like right after class. And then put the boys to bed, and I was like, there's so much that I wanted to get to, we didn't get to. So I stayed up till 2, writing these extra credit problems, and they're really cool.
There's
So-
3.
There's 3 of them, and I thought, you know, man, this is my last farewell to you guys, as you know, a math. The last time I'll be your math teacher. Been with you guys for 3 years. I owe it to you. So there are some. The first extra credit problem is cool. Yeah, that's pretty cool. The second one is wicked cool, and the third one is wicked cool. It's, I mean, like, it ties up, the third one especially, ties up a bunch of stuff that I've alluded to for the last 3 years, that we touched on briefly but didn't have time to really get into, and I thought, man, I owe this to you guys. So, it's long, but it's so cool, and I really hope you guys, like, I took a lot of time to do this. I hope you guys, like, if nothing else, you don't even have to do the wrong one. Really, the third one is really long, because I have a bunch of equations, and I'm just showing, like, look, this is the same thing as this. And so, but it's really long. I put a lot of work into it, and then at the very end, it's like, just do this, and it's so simple. It's like the simplest possible extra credit that, you know, I could give you. But the point, I would really appreciate it if you guys read it, because,
Yeah.
you know, and actually, like, give it, like, try to. You'll get more out of it if you kind of follow along and go, okay, yeah, I see that, you know, with pencil and paper, and try to figure that out. But, yeah, it's. Especially the third one. But the second and third extra credit problems are just really cool, and I hope you enjoy. So, any questions before we're done for the end of math with Justin?
How many problems are there?
So many! So many! It's terrible. I feel terrible. 16.
Okay.
Although, one of them...
Including the extra credit?
No. Not including the extra credit. These are 16 that you have to do, and then you have 3 extra credits that are optional. Although, one of them is like, if you have a pulse, you could answer this one.
One of the extra credits or one?
No, one of the actual problems. I think problem 12. It's like if you could read, you could do 12 with whatever your non-dominant hand is. You could do it with that. Again, there's lots of words here, right? Because I'm giving you like an extended word problem, like numbers 11 through 15 are really one problem. It's just that I've broken it up for you because I care about you. Stuff like that. A lot of these are very simple. Well, some of these are very simple, and yeah. Oh, it's gonna be hard, man. There's some hard stuff in here. Good luck. Sorry. No. Any other questions?